Okay, now we are going to learn about the formulation of the gyroscope. So uh, it doesn't have to be gyroscope, any object which is rotating. It has their own uh, moment of inertia and also angular momentum and also rotational or angular speed. So when we consider an object with complex rotational motion, so for example, it has its motion is in various axes. So we can combine all of them and in terms of omega right here. So omega is equal to the component of the speed. So we can uh, divide the speed and categorize them into three direction or three axes. The first is x, y, and z. Okay, so this how to replace this component. But before that, I, j, and k is the symbol for vector. So I, j, k is uh, just to tell you that these are vectors. Okay, so we need to base on this diagram, the third diagram. But if you remember, I said that we don't uh, in the next slide actually. Uh, if the top is oriented so that an instant at an instant the spin angle equal to 0. So we consider that the spin angle is equal to 0. So we can actually ignore the spin angle. So we can ignore the C. What I mean with C is the symbol C. Okay, or psi. I'm not sure, but it's this one is the another one is psi as well. So maybe this is C. Okay, so we can ignore the C. Okay, but in this case, before we eliminate the C, we include it first. Okay, so first we look at the speed according to x-axis. So x-axis is this one, or this one if we consider the spin. Okay, so the theta or the nutation is rotating about x-axis. Okay. Okay. What about so that's why we have our first component to be theta dot. So the omega in x-axis is the theta dot itself. There's no other angle involved. Okay. So now we go to the second axis, which is y-axis. So we look at it right here. So if you look at here, y-axis actually depend on the spin, the theta, and also the precession. Okay, the spin, the nutation, and the precession. Okay, so if you look at here, okay, why there's no psi right here? We can go back to that component after this. So we go to the third component, which is in z direction. Okay, so in z direction, right here, what are the component involved? So z direction is actually depend on the precession. Okay, because precession is right here. When we have nutation, so the spin is actually uh, a component of the precession. Okay, and also the spin itself. So that's why we have uh, the three component right here: psi, theta, and also C. Okay. Okay. If you look right here, um, this z-axis and this y-axis is perpendicular, which is 90 degrees apart. So when if you look at this rotation, which is the speed is c dot, okay, this is perpendicular to the y-axis. So there's no effect to the y-axis. It's not this z c is not a component of y-axis. It doesn't contribute to rotational in y-axis. Okay, so that's why in y-axis there's no c component. Okay, hopefully we understand that. So these are uh, the components for the speed of the angular speed of the top of the object. Okay, now we want to uh, ignore the spin, and the spin is considered to be zero. Or I mean, is the angle is zero, so c is equal to zero right here, and also the speed. So we can replace this c with zero. So the omega, this big omega, is when we remove the consideration uh, of the spin. Okay, and usually for this big omega, uh, this is related to the precession. Okay, so now if we compare this one and this one, the first and second component is the same, but the third component there is no c. Okay, very straightforward. Okay, so these are the reference picture. And now we want to consider the moment of inertia and the angular momentum, the moment itself. Uh, what are the moment involved in each axis? So when we consider x-axis, these are the moment that involve. Okay, what I mean with the moment is, what is I? I is the moment of inertia of this object. But remember, for an object, the moment of inertia for the same object, but for different axes will be different. So since if you look at here, ixx can be equal to iyy. Okay, why is it? Because if we go back to this, we look at the second diagram, because we already ignored the c. So the top is 90 degree to y-axis, okay, and the top is 90 degree with the x-axis as well. Okay, so that's why this top is has the same moment of inertia, because the motion of this top is the same. I mean, the moment of inertia, the shape of the top is the same, where the bottom of the top is touching at the zero. Okay, and that is the point where it touches the axis of y and x. Okay, so the moment of inertia of this top for y-axis and x-axis is the same, but for z-axis, z-axis, it is not similar, because it's rotating about the center of the top. Okay, so the moment of inertia about that axis is different. All right. So first we consider, I think I don't have to go through into detail about this formulation. Uh, if you need to understand this, I can explain to you, but I don't want to confuse you with this because we are not going to understand. No, we are not going to into details, and we are not going to use this equation anyway in your exercise. So what I mean, what do you need to understand is for moment about x-axis, mx, this is the moment of that object, of the top, this one, about x-axis. Okay, while moment about y-axis is the same. This moment about the x-axis. Okay, and moment about the z-axis also, which is the moment act on that axis. Okay, but there's no a moment about z-axis right here. Okay, and if you look at here, even moment about x-axis, we have component of z, and I is equal to ix and iyy. Okay, it's the same. So all right, so iz is izz. Okay, so in x direction, we also need to consider a z because z is the component of the moment. The moment contribute to the this moment contribute to the moment about x-axis. Okay, and afterward we can simplify them. Okay, right. Each moment summation applies only at the fixed point 0 or at the center of mass gravity. So in our case, we use point 0 as the center of the rotation. Since the equation represents a coupled set of nonlinear second order differential equations, okay, nonlinear second order differential equation, hopefully you understand that. In general, a closed form solution may not be obtained. So it's not a straightforward problem or question or equation. So we need to do some calculation, a lot of calculation to obtain the final answer, which is the speed, the angular speed of the top overall, the overall angular speed of the top. Okay. Instead, the Euler's angles may be obtained graphically as function of time using numerical analysis. So you need to use computer. You need to use calculation using computer, and a lot of function, a lot of equations should be involved. Okay. So you can calculate it manually. You need to use numerical analysis. Okay, to make our life simpler, and usually in our daily life, uh, and to be specific in our course, we will not consider the complex problem. And what we usually use is a special case where the precession is steady, which means the speed of the precession is constant, and the nutation angle, okay, the nutation angle is constant. I said just now precession is constant, and the spin also constant. So it's very easy. Okay, very easy. Okay, we want to learn the basics, so we make all of this constant. But in some case, in some question, we may change the nutation angle for different for example, in question 1, the nutation angle is 30 degree, and for B, nutation angle is 20 degree, for example. So it still be a constant. All right. So after we decided that, so what happened is the moment about y exists and moment about z exists is equal to 0 because the all of them are constant because of the condition that we have set just now. Okay, and the only equation that we need to consider is moment about x exists. All right. Why moment about x exists? Because that is the axis of nutation, the tilting of the top. So we further simplifying it. So okay, this component is considered as the omega z, the spin, this the spin angular speed. Okay, and we can simplify it even more. Okay, and we get this. And afterward, this question is useful. So if you have a different value of nutation angle, you can put the value in here, theta, and we'll get a different value for the moment. Okay. So note that the effect of the spin has on the moment about the axis. Okay, right here, the moment is affected by the spin. So when you increase the spin, the moment will increase. Okay. Same goes with the precession. When the precession is increased, the moment will increase. Okay. Now we want to make our life easier. So we make theta equal to 90. So this is in some question we will use this condition, but in some question we use other value of theta. So this is just for one example. So when theta is equal to 90 degree, the equation can be very simplified like this. Okay. So from here, we put theta equal to 90 degree. So this one will be 0. And what left is, this one will be 1. What left is Iz, omega z, and psi dot. Iz, omega z. Omega z is replaced by the c dot. Okay. And remember, c dot is the angle. And also, the psi dot is equal to omega. The omega is the speed of precession. This big circle. And omega z is the spin of the object. Now we can see this is the equation that I've shown you previously. This one, but this one is not correct. Actually, we have the corrected one where we have omega, we have the spin speed, but never mind. We go back to the equation. Okay, so remember, so what will happen if okay, so if you look at here, omega, the sigma m is actually the weight of the disc and also the rod. Okay, multiply with the radius. So we want to find the moment about this point, about this axis. So this is the omega sigma mx. Okay. So in order for this gyroscope or disc to maintain its position in 90 degree, so the precession and the omega z should have enough value to counter the moment about x axis. Okay. So okay. So if we have very high spin velocity, speed, so the precession will be slow. Okay, the precession will be slow. But if the spin is low, the precession should be faster. Okay, all right. But what happen if we add weight right here? What happen if we change the disc uh, with uh, another disc which has higher weight? Uh, what will happen? The spin is constant. We cannot change the spin, but the precession will automatically increase. The precession speed, the omega, this omega will increase. It will move. We will rotate faster. But uh, just for an example, if you rotating a small top, okay. So when uh, when it's about to drop, I mean when it's about to the energy is about to finish, about to dissipate. So it will rotate very quickly with high precision, and finally it stop. Right. When it is stable, the precision is slow. The precision is slow. It rotates slowly. But when the energy, because of friction, the energy is reduced, and finally the top will rotate quickly, and finally it will stop. All right. So that is the simple example for you to understand. One would expect the rotor to fall under the influence of gravity. So we have mentioned just now, because of this 90-degree, it seems like impossible for this to hanging like this and without dropping downward. But it is logical after we consider the angular momentum. Okay. Okay. This unusual moment is referred as the gyroscopic effect. Okay. Studying the action of the gyroscope, or known as gyro. A gyro is a rotor that spins at a very high rate about its axis or symmetry. So usually when any application use gyroscope, uh, uh, the disc that rotated should have high mass. Okay, it should have high mass, and also it will be rotated with very high speed. That is to ensure stability of the gyroscope. Okay, because with high mass and high speed, it will we will have high angular momentum, right? Because angular momentum is depend on the speed and the mass, right? Okay, this rate of spin is greater than its precessional rate of rotation about the vertical axis. Okay, usually the spin is greater. This the spin and the rotational speed is greater compared to the precessional speed. Okay, but when the spin is and when we reduce the spin speed, the precession will automatically increase, like the top that we just explained just now. Hence, the angular momentum of the gyro can be assumed directed among its axis of spin. Okay, that's for the gyro rotor omega z. So this is the spin when it's far bigger than the precession, and the magnitude of the angular momentum about 0.0 reduced to the form HO. This is the angular momentum equal to Iz omega z. So because of this is from the equation right here. but because the precession is very low and the spin speed is very high, we can ignore the omega y. Okay, so omega y is not right here. So HO will be the angular momentum. Since both magnitude and direction of HO are constant, as observed from the XYZ direct application. So, okay, as observed from the XYZ direct application yields. So, okay, so this is the new formula. If you look at right here, okay, it just based on the same formula right here, and this one is replaced by HO. I mean, IZ and WZ is replaced by HO. Nothing new, huh? Okay. Omega Y always swings HO or WZ towards the sense of sigma mx. Okay. So I have explained to you about this. So this is the direction of precession. In effect, the change in direction of the gyro's angular momentum, dHO, is equivalent to the angular impulse caused by the gyro's weight about 0. Okay, so this equation, the dHO is equivalent to the angular impulse. dHO is the angular momentum, the change of angular momentum. Uh, so is equivalent to the angular impulse caused by the gyro's weight about O. So we add dt right here. So when moment, angular momentum times time. So this is the angular impulse. So this is the equation for angular impulse. Okay. So this is just to show you the relation with angular impulse. All right. So uh, now we look at this gyroscope. We have gyro at the middle, and we have gimbals, two gimbals, and we have bearing to reduce the friction. Okay. So in this case, the gyro or the rotor or disc is supported at both direction, which is both end of the shaft. So in this case, there will be no external momentums because both end is supported. So it becomes free of external momentums. Okay. So if you rotate the gyro in any orientation, and you rotate the gyro with high speed, so it will maintain its position. And when you lift this block along with the gyroscope, and when you move it slowly to the right or to the left, you turn it, the gyro will tend to maintain its position. So right now it's in horizontal plane. It's in horizontal plane. So when we move this gyro, when we move this block, the wooden block, the gyro will try to maintain its position in horizontal plane. Okay. So in theory, its angular momentum h will never precess. Okay, for this one, it will never precess. It will stick to the initial position, but instead of maintain its same fixed orientation, along the axis of spin when the base is rotated. Okay, so it will fix to the initial orientation. This type of gyroscope is called a free gyro. So we have free gyro and we have uh, maybe we can call it forced gyro. It's like vibration, free gyro and forced gyro. I don't know whether that is the correct name, but for this one it is a free gyro because there is no precession. And this one is useful as a gyro compass when the spin axis of the gyro is directed north. In reality, the gimbal mechanism is never completely free of friction. Of course, we have bearing, but bearing we can know the bearing friction, but of course it is far uh, the friction is far lower when we use bearing. So we can minimize the friction. So such a device is useful only for the local navigation of ships and aircraft. But in our current aeroplane, we don't use this type of gyroscope anymore. We use, I forgot the name, laser something. Gyroscope. The name is still gyroscope, but it is based on laser. Okay, and also we use for other type of application. We use like a sensor, a chip. Uh, I have seen one type of gyroscope in electric electronic electronic block, and it is very small, just a sensor. So that one is enough to detect the orientation of an object. For example, in this phone, uh, when you raise it, it can detect that I have raised it. Even in your watch, you can have a gyro inside that, but we don't call it gyro, maybe a sensor. When we rotate this phone, it will know that we have rotated 90 degree and it will turn the screen. So we have gyroscope in our phone. So hopefully you okay. About your assignment, I will explain it later. Okay. For now, I want to finish with this lecture. So that is the some examples of gyroscope, but this kind of gyroscope is no longer popular. But that's the basic gyroscope that you can learn. But in other application, uh, which is not maybe the forced gyroscope or the forced gyro, we can apply it in so many situations. For example, in wheels, in your car wheels, in your motorcycle wheels, in a gearing system, there will be unwanted gyroscopic effect. For example, the precession. We don't want the precession in our gearing system. It will uh, disturb the system. It can cause damage or non unalignment. Okay, so we don't want uh, gyroscopic effect. So we need to learn about gyroscope. Okay, so the gyroscopic effect is also useful as a means of stabilizing both the rolling motion of ship and seas. Also, I've already mentioned this before this, and also missiles and projectiles. Okay. Furthermore, this effect is of significant importance in the design of shafts and bearings for rotors, which are subjected to unwanted precession. So this is the one that I mentioned just now. Okay, now we continue with example so that we can understand more about how to solve gyroscopic motion problem. So for the first example, um, the top shown, there's a little diagram down there, has a mass of 0.5 kilogram, and is processing about the vertical axis at a constant angle. So this is the vertical axis, and the angle of nutation is theta equal to 90 or 60 degrees, sorry. If it spins with an angular velocity 100 radian per second, okay, determine the precessional velocity omega p. Assume that the axial and transverse moment of inertia of the top are 0.45, okay, time 10 power of negative 3 kilogram meter square, and 1.2 time 10 power of negative 3 kilogram meter square respectively. Okay, so what do we need to determine is the precessional velocity, and given is the other details and also the moment of inertia. So what is axial? So axial moment of inertia is the one that we measure from this axis, so the spin axis. So that is the axial moment of inertia, while transverse moment of inertia is the one that we measure from x-axis, which is not shown in this diagram, which this one, x-axis and also y-axis. So both are 90 degree apart from the z-axis right here. Okay, so both moment of inertia about x-axis and y-axis has value 1.2 power 10 power of negative 3 kilogram meter square. Okay, so we can assume that the motion is steady precession if there is no mentioning about the change of the nutation, the change of the speed of precession. So we can assume that the condition is steady precession, where the nutation is constant, the precession is constant, and also the spin is constant as well. The coordinate, okay, now we continue. The coordinate axes are established in the usual manner, that is with the positive z axis in the direction of spin. So this one is the direction of spin. The positive z axis in the direction of precession. So z axis is the axis of precession, and the positive x axis in the direction of the moment. So the small x, do not get confused with the big X. Okay, again, the big XYZ is the original position, the Cartesian coordinate, while small xyz is the axis which follow the object orientation. Okay, so the nutation is the rotation of the nutation is about x-axis. So this is 90 degree is about x-axis. Okay, so the moment also in the direction of the x-axis. Now we can use the equation for moment about x-axis. So I have mentioned to you previously where the moment about y and z-axis can be ignored uh, if the condition is steady precession. So we can just consider about the moment about x-axis only. So this equation you can get it in the previous slide, and uh, you can have a note for this formulation, so you can use it when you answering any question. Okay, so first we look at the sigma mx. So what is the torque or moment uh, created by the top uh, due to the weight of the top? So we go back to the question. Okay, the top has mass of 0.5 kilogram. Okay, so the moment created about x-axis is 4.905. Why 4.905? Okay, because that is the weight. 4.905 is the weight. 0.5 times the gravitational acceleration, and the length from the center of gravity of the top to the point O is 50 millimeter, which is 0.5 0.05 meter, if I'm not mistaken. So 0.05 meter. Okay, and why sine 60? So the notation is 60. So we just consider the vertical value. Oh, no, we are considering the horizontal length. So the length from this point to this axis is the one that we need to calculate the torque. So the weight is vertical downward, and we multiply with the length from the center of the uh, yes, from axis, the vertical axis to the uh, center of gravity. Okay, so when we multiply them, we can get the moment that created by the weight of the top. And then we need to calculate the counter uh, gyroscopic effect, or gyroscopic what you call it, angular momentum, uh, in order to counter the torque created by the weight of the top. So we put all value that we have known from the question. So make sure you put the value correctly. This is transverse moment of inertia. This is axial moment of inertia, because Iz is about the spinning spinning axis. Okay, so it is the axial moment of inertia. Okay, so right now what we want to calculate is the psi dot, which is the speed of precession. So we can put theta, we can replace theta equal to 60 degree, and we can replace the C equal to 100. Okay, and also for the moment of inertia of transverse moment of inertia, also we replace them. Okay, and I think that's all. And then we simplify them, we can get this quadratic equation. And from here you can calculate it using your calculator to find what is the value for psi dot. Okay, and the final answer is right here. So actually we can have two answers for any cases, two answers is possible. So you can give two answers. So you can we call it uh, define the answer if the bigger one for high precision, okay, and the lower one is for low precision. Okay, hopefully you get you understand how to solve this problem. Now we go to the next example. Okay, the 1 kilogram disc is spinning about 8 axis with a constant angular velocity. Okay, this the brown disc, the angular velocity is 70 radian per second. The block B has a mass of 2 kilogram. Okay, so by adjusting its position, when we adjust the position along the shaft or the rod, so the position is S. So one can change the precision of the disc about its supporting pivot. So when we adjust B, the precession speed can be changed. Okay, so determine the position S, which will enable the disc to have a constant precessional velocity equal to 0.5 radian per second about the pivot. Okay, so this is the speed that we want to achieve, and other parameter is important. So now we can solve this problem. So the first thing is we need to calculate the moment created by the wing. So as shown from free body diagram, the origin for both XYZ and big XYZ coordinate system is located at point 0. Okay, so point 0 is marked as the origin. Okay, in the conventional sense, the z-axis is chosen along the axis of precession. Okay, so we can, from this diagram, we need to decide which one is the axis of precession, which one is the nutation angle, which one is the spin axis, okay, the z-axis. Okay, so we can decide that because the precession motion is this way, therefore the vertical uh, line from the origin is the precession angle, which is the big Z axis, and the spin axis is the horizontal line along the shaft. So that's the small z. So that means the nutation angle is 90 degree. Nutation angle is 90 degree. And then, so that's all that we have to decide about the coordinate system. So like I said, nutation angle is 90 degree. In the conventional sense, the z-axis is chosen. So this is the one that we have decided about the axis. Okay, since the precession is steady, so we can use the simplified version of the moment about x-axis equation, and also this is because of the nutation angle is equal to 90 degree. So we have instead of the long lengthy equation we used in the previous example, we can use this formula. Actually, you just put the 90 degree right here into the theta, right here, and you will get the same equation. So sine 90, sine cos 90, some of them equal to 0 or 1. So you will get, finally you will get this formula. Okay, or just simply use this formula if theta is equal to 90. So for the right hand side is quite straightforward, where you know already the psi dot, which is 0.5 radian per second. So this is the speed that we want to obtain. So the moment of inertia about the spinning axis. So 0.05 is the radius of the disc right here, 50 millimeter. So we want to know the moment of inertia of the disc. So this is the formula. One is the 1 kilogram weight of the disc, and omega z is the spinning speed. So we just put 70 over there. Okay, and now we go to the left hand side. These are the moments involved in this system. So the first one is the disc at the left hand side right here, and another one is the block. So for the disc, 9.81 is the weight. So 1 kilogram times the 9.81 gravitational acceleration. So we get 9.81 Newton. So we multiply with the distance from the origin, 0.2, from the pivot, 0.2 meter. Alright. So this is the value that we still don't know. Okay. So these are the moment created by the block. So I just write that M block. Okay. So we solve this problem, solve this equation, and then we will get the final value is negative 1.9183. So both sides has negative sign, so we can cancel them, and then we can replace the moment caused by the block, the 2 kilogram block, with this force time distance equation. So the distance is s, and the force or the weight is 2 kilogram times the gravitational acceleration. So we get 19.62. So we put this value to the right hand side, and finally we get the distance. So s is equal to 0.0978 meter, or 97.8 millimeter. So this is far closer right here compared to this one, which is 200 millimeter. Okay, so that's it. We got the solution already. Hopefully you understand both example. Thank you very much for your attention. Assalamualaikum and have a good day.